A radiogenic nuclide is a nuclide that is produced by a process of radioactive decay. It may itself be radioactive or stable. Radiogenic nuclides form some of the most important tools in geology. They are used in two principal ways. In comparison with the quantity of the radioactive parent isotope in a system, the quantity of the radiogenic daughter product is used as a radiometric dating tool. In comparison with the quantity of a non-radiogenic isotope of the same element, the quantity of the radiogenic isotope is used to define its isotopic signature. This technique is discussed in more detail under the heading Isotope Geochemistry. Examples: some naturally occurring isotopes are entirely radiogenic, but all these are isotopes that are radioactive, with half-lives too short to occur primordially. Thus, they are only present as radiogenic daughters of either ongoing decay processes, or else cosmogenic processes that produce them in nature freshly. A few others are naturally produced by nucleogenic processes. For radiogenic isotopes that decay slowly enough, or that are stable isotopes, a primordial fraction is always present. Since all sufficiently long-lived and stable isotopes do in fact naturally occur primordially, an additional fraction of some of these isotopes may also occur radiogenically. Lead is perhaps the best example of a partly radiogenic substance, as all four of its stable isotopes are present primordially, in known and fixed ratios. However, 204 petabits is only present primordially, while the other three isotopes may also occur as radiogenic decay products of uranium and thorium. Specifically, 206 petabits is formed from 238 U, 207 petabits from 235 U, and 208 petabits from 232 Th. In rocks that contain uranium and thorium, the excess amounts of the three heavier lead isotopes allows the rocks to be dated, or the time estimate from when the rock solidified and the mineral held the ratio of isotopes fixed and in place. Other notable nuclides that are partly radiogenic are argon-40, formed from radioactive potassium, and nitrogen-14, which is formed by the decay of carbon-14. Other important examples of radiogenic elements are radon and helium, both of which form during the decay of heavier elements in bedrock. Radon is entirely radiogenic, since it has too short a half-life to occur primordially. Helium, however, occurs in the crust of the Earth primordially, since both helium-3 and helium-4 are stable, and small amounts were trapped in the crust of the Earth as it formed. Helium-3 is almost entirely primordial. The global supply of helium is almost entirely radiogenic, as shown by its factor of 10 to 100 times enrichment in radiogenic helium-4 relative to the primordial ratio of helium-4 to helium-3. This latter ratio is known from extraterrestrial sources, such as some moon rocks and meteorites, which are relatively free of parental sources for helium-3 and helium-4. As noted in the case of lead-204, a radiogenic nuclide is often not radioactive. In this case, if its precursor nuclide exhibits a half-life too short to survive from primordial times, then the parent nuclide will be gone, and known now entirely by a relative excess of its stable daughter. In practice, this occurs for all radionuclides with half-lives less than about 50 to 100 million years. Such nuclides are formed in supernovas, but are known as extinct radionuclides, since they are not seen directly on the Earth today. An example of an extinct radionuclide is xenon-129, a stable isotope of xenon which appears as a relative excess against other xenon isotopes. It is found in meteorites that condensed from the primordial solar system dust cloud and trapped primordial iodine-129 sometime in a relative short period between the iodine-129's creation in a supernova and the formation of the solar system by condensation of this dust. The trapped iodine-129 now appears as a relative excess of xenon-129. Iodine-129 was the first extinct radionuclide to be inferred, in 1960. Others are aluminium-26, and iron-60. Radiogenic nuclides used in geology. The following table lists some of the most important radiogenic isotope systems used in geology, in order of decreasing half-life of the radioactive parent isotope. The values given for half-life and decay constant are the current consensus values in the isotope geology community. ** indicates ultimate decay product of a series. In this table, year equals giga-year equals 109 year, MYR equals mega-year equals 106 year, KYR equals kilo-year equals 103 year. Radiogenic heating. Radiogenic heating occurs as a result of the release of heat energy from radioactive decay during the production of radiogenic nuclides, along with heat from the outer core of the Earth. Radiogenic heating occurring in the mantle make up the two main sources of heat in the Earth's interior. Most of the radiogenic heating in the Earth results from the decay of the daughter nuclei in the decay chains of uranium-238 and thorium-232, and potassium-40.